Okay, welcome to lecture 13. Today I want to start by describing problem set 3 a little bit, and this is the kickoff to problem set 3. Most of the material for problem set 3 should be on the website. You have a specification for the Gnutella protocol. You have a description of the problem set, and you have your group assignments. Well, first of all, the purpose of this is to form a distributed file sharing network. So you can put your files on the network and other people can share them, and you can search for files that might be of interest to you and download them on your machine. And unlike Napster, Gnutella is a very general system and will let you search for more than just MPEG files. So you can search on for any type of file. So you basically give it a pointer, the program, when you start it up, you give it the name of a directory on your local file system, which you put the files that you want people to share. It doesn't just because you're running this, it doesn't give people access to your entire machine and your entire file system. At least it shouldn't if you write it correctly. They should be restricted to just the files in a given directory, or maybe the files in that directory and all the subdirectories of that directory. Okay. You then give it a different directory, or a directory which could be the same, could be different, which is where you want to put any files that you download from the world that you think are interesting. The other thing you give it is a internet address to some other node. Okay. Out in the world at any given time, there's a whole network of Gnutella nodes functioning. Okay, and they are connected to each other and passing messages around. And in order for you to link in, you have to give it the internet address of one of the nodes so you can get connected in. So once it has these pieces of information, the program starts up. It attempts to make this connection, and if it succeeds, it's ready to go. And the functionality that from the point of view of the user sitting in front of it, the user can initiate searches, and a search will searches are based on keywords, like in an internet search engine, and that search will propagate through, and the network will return to you any files that match that keyword search. Now, the search, unlike the searches in the internet, are not done on content, or the searches on the web search engines are not typically done on content, but merely done on the file name. And all we're going to ask you to do, at least for this first phase, when you're responding to searches, is search on the file name. So any keyword that matches a portion of any file that you're agreeing to share is considered a hit. Okay. So you can ask this network to follow this, to search for some files with some keyword. Okay. Now, the way the network works is, since there are a large number of machines out here and they're connected in ways that no one, in ever-changing ways, you don't want to just search this machine, since that would be you want to get access to more than the files that this machine only is sharing. But you don't want to propagate this message through the entire network, because you would just generate tons of traffic. So the way Gnutella mediates this is with a counter on your messages that has what's called a time to live, TTL. So when you send a search to this node, it will decrement the time to live, and if the time to live is greater than 0 still, it will propagate your search to all the nodes it's connected to. And they'll decrement and propagate and decrement and propagate. So eventually, the time to live will hit 0, and your search will not propagate any further. So you're actually not searching the entire network, but you're searching some subset of it out to the horizon of your time to live. And the typical time to live seems to be 7.
So that's just the depth of the nodes?
That's just the depth out in the network, the number of forwards that any message can do. That keeps the network traffic from bouncing around and just growing.
There's nothing, though, to prevent us from hitting the same node multiple times on one search by it getting branched through
different paths coming through.
Yeah.
There might be, I don't know, you'll have to read the spec in more detail to see. There's certainly enough information in the packet to tell whether you've seen the search before. And so I guess it's up to you whether you want to keep that information around and how long you want to keep the information around and then not propagate it. But
so when it decrements the time to, what did you say?
Time to live.
Time to live. Does it also send off like a packet saying, okay, these are the 3 that we've searched up till now, and we have 4 more searches to go? Does it say that it searched these 3 nodes?
No. The only time it responds to you is with successful hits.
Okay.
So when you've got a successful match, the matching node will send back the name of the file and the node it's on back to the client. And this program, the servant client, whatever, will display the list of current hits, current matches. And you can then download, request, after examining them and where they came from, and, they also send other information like how fast they think their network connection is to give you an idea of how long it'll take to download them. And then you can request to download a given file on a given machine. And that means you establish a direct connection now, not going through this path, from the node that you want to download from to your node. You do one of these connects, and you use the download protocol. And the Gnutella download protocol is just the HTTP GET protocol. So you can you issue essentially an HTTP request, and if all goes well, the file will be returned to you. Now, this node could also reject you, send back an error. You could find that this node is actually inaccessible if it's behind a firewall or doing some kind of IP masquerading. I suspect that our nodes will be inaccessible from the outside world for connection to download from us. But you should be able to all talk to each other. And certainly from the test clients we've downloaded, we've been able to download from the outside world. It's not clear that anybody's been able to upload from us. But we're also able to participate in the searches and forwarding. So pretty much I've described what this does as a client. Now it's also functioning as a server. So it's listening on some port all the time, and the port is usually 6346, I believe, is the standard Gnutella port. It's waiting for connections on this port, and when people to link it into the network, and also it's listening for requests coming in, and it'll once you start up, if you're really connected, you'll get a steady stream of searches coming in that you will check against your database to see if any of your files match, and send back replies if they do, and forward the messages on to all the people that you're connected to if the time to live in that message hasn't hit 0. So all this is detailed in the protocol spec, which we gave to you. And there are some sample clients that you can try to get an idea of how it's supposed to work. There's 2 that we've set up both in Java. One is called Fury, which is an open source client, but I would prefer you do not use any of their source in your project. Just to give you an idea of, well, anyway, the second one is called LimeWire. It's free to download, but you don't get the source to it. So,
These were Java or?
These are both Java ones. There are a bunch of other non-Java ones, but I don't know of any that run under Linux. There's a lot of Windows ones.
Another one called Gnutella.
Right,
Java.
which I have not found, but right, that's another Java one. I don't know of any native Linux one. There was for a while a GTK Gnutella effort going on, but that seems to have stopped. I think the people doing it just had to do other things.
You can't see the names of the files or anything these other nodes, can you?
Not unless they match one of your searches.
You can't go and look through their directory.
Well, once you've gotten a connection to someone, there is, I believe, a command that lets you browse the directories of, you can browse the shareable files of a particular node. You can ask a particular node to show me everything you're willing to share, and it should send it to you. So, but you can't browse their whole directory tree, only, unless they were sloppy, only the, right.
What kind of files are on this network?
Stuff. Yeah, just stuff. But these peer-to-peer networks are kind of an exciting architecture, and there's a lot of issues in designing the network architecture of this. It's a challenging thing to do. It's not clear Gnutella actually got it right, but they at least have an existing network so we can test against it, a bunch of reference clients, and a written spec. So it saves the staff and myself from having to design a network protocol, which will probably be worse than theirs. So there's another protocol similar to this, or another network similar to this called Freenet, and its goal is to do this sort of thing, but preserving anonymity. This network in design does not preserve anonymity. Freenet's goal is to preserve anonymity in the network.
Is there any issue with virus? Like you can download files, it's really a virus?
Well, all you're doing when you download the file is writing a file.
Yeah.
Okay, so unless you run it, if you download an arbitrary executable and then run it, you're on your own. So be a little careful there.
Are there viruses that can be stored in MP3s? I know I've never heard of that. So that when you run the MP3 or play it.
I don't know. That would be, dependent on which MP3 player and whether there's holes in the MP3 player that a virus writer could exploit. I don't know of any, but I can't guarantee that there aren't any either.
Just one question. How do you connect to the first node? How do you know?
Yikes. The first node, you basically just have to know a pointer to something on the network. Okay, so there's lots of ways you can find that out, either by news groups or whatever. There are also a bunch of Gnutella kind of host servers, which are lists on the web of port numbers and IP addresses to try.
Do you get multiple links? What happens when your link goes down, or if you're...
Right, well, one of the things you can do once you connect is ask the thing to go get more links, the IP addresses of more nodes. So you typically, once you've got one connection, start to build up a bunch. So as, your main link goes up and down, you always have some link active. That, of course, increases the network traffic because it increases the number of links you're forwarding over, but it keeps the network connected. So, like I say, these architectures are tricky. It's tricky to balance lots of things. So this is a substantial design project, and to be perfectly honest, I don't know how difficult it is. So I believe it should be doable in the groups you have, in the amount of time you have. And what we're going to do is monitor progress closely. Basically, if you're whipping along really fast and going to have it done, we'll do a PS4, which will be some kind of add-on to this. If it looks like the problem is sufficiently hard that there'll only be 1 or 2 days to spare by the time everyone finishes, we probably will come up with some other scheme. So we'll be tracking everybody and see how hard it is. To give you an idea of the scale, Fury is probably around 150 classes, 150 class files. Now, most of those are very small. It seems to be a very object-oriented design, so a lot of those are GUI handlers and various action handlers, and only contain, maybe 20 to 50 lines of code. So, I don't know. I would estimate maybe a couple thousand lines of code for the entire project, but lines of code is not a very good measure of complexity. If you pay somebody by the line of code, you'll get lots of lines of code. So So today, the rest of today, I want to talk about the software design process, especially as it relates to larger group-oriented projects. This is kind of the small end of a group software development project. And, they would scale up to here from things that would take, a team of 4 to 6 or 10 many months. So I want to talk about the process, some aspects of which would be relevant to you in this project, some won't, and then some tools that are useful and some concepts and way of doing things that are useful. These are my stages. People's notions of how software project management should go, vary according to their experience, the size of the project, and there's many books that will written on the subject that will give you advice about how to do it, but it's a difficult thing to do. You've basically got to coordinate the efforts of lots of people and at the same time do a complex technical task. So there's social elements, there's technical elements, and it's a difficult thing. So the 3 phases I want to talk about are specification, implementation, and testing. And these kind of run in sequence. At least when you start them up, you're starting up in sequence. But once you're far along in the project, they're all kind of going on in parallel. So that makes the whole project more challenging. Some people would include an additional stage called design. I think that there's one level of design in here. Each one of these actually has its own notion of own design phase in it, as well as actual doing stuff phase and producing the output. The specification stage is when you decide what the thing is supposed to do and how it's broken up at the highest levels in terms of how you're going to describe what it's supposed to do to your customer or your client. If it's a piece of shrink-wrap software that you're going to install, that's kind of userware, that the specification would basically consist of the list of tasks it performs, what the user interface looks like, and its behavior from the point of view of the user. All right, so what comes out of here basically is some set of specification documents, okay, and design documents. If you are designing a modular subsystem or a modular system of libraries for people to use, your specification would be how somebody would take your library. It would essentially be API documentation, what procedure calls or method calls they would make on your library, what your library would return. If your library is part of one of these software stacks, like it often is, okay, and here's you have to tell the people up here what you're going to look like from the top, and then you have to tell the people below you how you're going to interact with them in the sandwich, and then other people will build that part and hook you in. This specification part is one of the most difficult parts of the process for several reasons. One is that you're designing it essentially open loop. You have to make a bunch of decisions about how you want to break your system up into pieces, what the important functionality is, what the interface, the major interfaces on the top and bottom should look like. You have to basically design all that, but you really have no way of testing it because it's not built yet. So you really don't know whether you've made the right decisions until several months later when you've implemented it and tested it. So that's one of the things that makes this very challenging and very stressful, is because you have to bind yourself to a bunch of decisions that only down the road will you have any way to find out if they were the right ones. So in this phase, there's typically lots and lots of review processes. So you make a specification, you write it up in a document that describes, how somebody would use this thing. You then get a bunch of people who are not involved in the design to come and you present it to them and they poke holes in it, or try and poke holes in it. And you iterate around that a couple times, and that's a very useful way of refining your specification, seeing if it's correct or not, or if it has a chance. If you're lucky enough to have something that has some theory behind it, it's very nice to be able to prove correctness using some kind of mathematical modeling. In some sorts of protocols, you can actually prove that something is safe or efficient, or so there's a whole field of computer science which is basically proving theorems and correctness of these sorts of designs. Another thing that's useful if you don't have a theorem, you can fall back on a simulation and kind of fake it up and see if it performs roughly the way you think. Another reason why this is hard is because once you publish those specifications, okay, if it's a piece of software, a library that people are going to use, some component, once you publish that, you're pretty much stuck with it for a very long time, okay, because people are out there using it, they've incorporated it into their products, these are your customers, they are depending on it, and if you say, we did this wrong, we'd much rather do it this way, in order to get them to change over, you have to wait till they're ready to upgrade all of their systems and all of their customers are ready to upgrade, and that time is measured in years to decades, and so you're going to support all the decisions you make in that specification phase for a long time. So it really pays to do this right. Now, unfortunately, doing this is outside the scope of this course, but I hope to inspire you to look at courses on network architectures and modular architectures and communications. And this is where all the theory that you learn tends to really come to bear, because it gives you ways to think about things without having to actually build them. Fortunately, in our project, somebody else has done all that work and given us a specification document, which is on the web, which is on our website. And so we're mostly concerned in this project with the implementation and the testing aspects of the problem. Now, the implementation, as we've said many times, starts out with another design phase. All right? In the previous problems that we had, they were you could basically start out the design phase by thinking of the steps it was going to do and go, and then build, think of the classes you were going to need and the data in the classes. This is a jump above that in complexity. So again, you need to write down and think about the various functionality you have to implement. But the first thing you probably want to do is take the entire set of functionality and design it or cut it up into various sub-pieces. So kind of not at the level of class, but kind of at the level of conceptual thing. Okay, for example, maybe the server part, the part that functions as a network server and handles server messages, is one piece. The GUI part would be one piece. The search part, all of these things which are much more than one class in size, but are the major components of your system. And then you want to talk about what the interfaces are, design what the interfaces are between them, how they communicate, whether they share data, whether there's a set of method calls between them. Okay, and then you've broken the problem up into smaller problems which are independently implementable, definable, and testable, which is the whole way you build big and complex things, is decomposing them into smaller and smaller collections of things until you finally get something that you can wrap your head around and actually build. So you would do this level of decomposition, and this gives you something you can document. So even before you would implement any of those pieces, you would basically document in the form of JavaDoc and maybe the class and interface definitions without any method implementations, what these things would look like to each other. Once you have that, then you can split these up into separate implementation groups. Since you have multiple people now on your project, you can divide up the work, put one person on each piece, or multiple people on some pieces if they're hard, or sometimes, it's just good to have two people working together, looking over each other's shoulders, one person typing and one person criticizing. I like to be the criticizer. And that's actually a legitimate programming paradigm. So we've already talked about in previous lectures how to further chew these pieces up into what classes you're going to need, and then going through and implementing the methods and the like. I want to talk about some of the social aspects and coordination aspects of when we're building a large number of classes and you have multiple people on your project. One thing to think about when you're building something this big is how you're going to arrange all of these source files. Okay, if you're going to be writing maybe 100 .java files, you probably don't want them all in one directory because it'll be impossible to find anything. Nor do you want to put all your code in like 3 files with lots of classes in it. So typically people start to divide things up into directory subtrees. So you have maybe a main project source directory, and under that you would have, for each module or piece you define, maybe you'd have a separate subdirectory, mod 1, mod 2. Okay, you'd probably give them more creative names. But and then these would be independently testable, and the people working on that would only work on those files, and vice versa, at least at the beginning. So that gives you a more, again, you're dividing a complex problem up into smaller, more manageable pieces. And so you might have something at the top level also, which has something with all your interface and communication files in it. There's lots of ways to divide it up. So if you get a source tree from the internet for any open source project, you'll typically see a directory tree under source that will look like this. Lots of different sub-pieces each corresponding to an individual library or a set of classes. Now Java kind of throws a wrinkle into this in the way it names things and looks for class files. So depending on how you want to build this thing and run Javac, Java has basically each directory is going to want to correspond to a package. And if you want to talk and use different subdirectories, you need to use this package naming scheme. We'll talk about that on Monday. I tend to cover a bunch of Java details which we kind of glossed over or just didn't fit anywhere. But remember all those things that you're including, like java.swing.star, okay? These paths represent, in the Java class world, kind of a package path, okay? So it's saying, or a class path, it's saying I want this package and this package inside there, and then all the classes inside that package. And Java maps these things onto file system directories. So when you actually say this, it goes looking for something somewhere in a directory, java/swing/whatever. So if you want to make your own packages, your package structure and your subdirectory structure in Java have to match. This is not true in other languages, at least not as strongly.
So in this current case, we would include src.mod1.
Or if you were compiling in here, you would just say mod1.star, mod2.star. You'd have to have imports for all those. And as we'll see, we'll have to put some labeling on here to, a package statement in all these files to get it to work.
So if I come with you mod 1, it wouldn't know the parent directory? Would it know the parent?
Yes, it always knows the current directory you're running Javac in as the default package.
Yeah, suppose you're in mod 1 directory.
Oh, and-
you know what's the source, or?
I don't think so. I think you would have to explicitly tell it by setting the class path variable. That class path argument to Javac is the thing that gives it all the root pointers to where to start looking for these relative things. Since it doesn't look for /java/swing, it's going to look for it in some class path off of your Java install. So that's something to think about. Another thing that is useful in implementing multi-person projects is source control. All right. If you have a lot of files and a lot of people changing the files, and sometimes you're making good changes and making things better, and sometimes you're making bad changes and breaking things, you would like to have a way of organizing who does what, and not have two people opening the same file in Emacs at the same time, and all those sorts of things that happen when people are trying to work on the same code base. In a small project, when you're doing it yourself, it's not such a big deal. If you're doing it just with the person in the cubicle next to you, you can coordinate a little better and just say, you doing this, I'm doing this, Once you get beyond that, where people are across the room or coming in at different hours and the like, you really need some way to coordinate. And so some sort of source control system is a good idea. It takes a while to get used to source control systems. At first, they just seem like a pain and something to get in the way and nuisance to counting, but they ultimately are a good idea. There are a number of schemes out there and products out there that do source control. There's one group that essentially allows, once you've set up a set of files you want to control, it lets people lock files to check out and work on them. Basically, you can give it a command that says, I'm going to work on this file, and it'll lock that file for you and not let anybody else work on it. I find those systems to be a nuisance because somebody else has always locked the files that you want to work on and have gone away for a long weekend. So you end up like copying something and cheating, and then it's a nightmare later on. There's other systems that are more graceful. All of the integrated development environments typically have some sort of source control system. Microsoft has one called Visual Source Safe. There's one called RCS for Unix. The one that I recommend, and I highly recommend you all use this, as a matter of fact, we will set up this for all of your groups. It's called CVS. Has nothing to do with the drugstore. But the URL I gave you in the notes actually does go to the drugstore. So search around on Google for the right URL. You found it, right? It's like CVS Home or something, or something. Yeah, but
Google search.
right. So
And source.
and source, right. CVS works in the following way. You have multiple people working on the project, each with their own version of the source. And CVS keeps in its archive the master version of the source. As a matter of fact, it not only keeps the master version, it keeps all previous checked-in versions, maintaining a whole sequence and time of your software as it changes and evolves. So this is called the repository, usually. And it's a bit of a nuisance to set up, but we will set them up for you. Once it's set up, it's fairly easy to use. There are 3 commands that you need to know to use it. One of which is called checkout. And what checkout does is take a fresh copy of the repository and expand it so it'll in whatever directory you run it in. So it'll basically give you a fresh copy of the source tree. There's one called update. Okay, this does essentially an incremental checkout. This goes out to the repository, looks for any files that are higher version number than the current versions you have in your directory, and it'll update your directory with all the new versions.
But if you'd made changes to your previously checked out version and then updated, it would throw away those changes that you made.
No, it's very smart when you update, okay? As opposed to checkout, which will overwrite. If you do an update and you've changed, your version is changed versus the one in the repository because you've improved things, it will merge the two, okay? And it'll make some determination as to whether that merge can be done gracefully and that it can just smoothly incorporate your changes into the source file, or whether there's a conflict, whether somebody else changed a piece of code, the same piece of code that you wanted to change in the same place, and so there's a conflict. In that case, it will alter the file when it updates your directory. It will give you, it'll put a bunch of things that look like this, then the old stuff, then a dash line, and a set of these, and the new stuff. So, and it will signal that in the update by giving you a big C in its printout, which means conflict. And when you see a file that has a conflict, you need to go look in, check to see what's different in the two versions that it's flagged, and clean it up. Basically get rid of one of these guys and make it so that you're happy with it. Okay? So it's very nice that way in that it doesn't force you to lock files between people trying to use them, but it lets everybody kind of work the way they want on their own copy of the file, and then nicely merges them back together again to the extent that it can. The final command is how you get your stuff back into the repository, and that's the commit command. And so you just say CVS commit this file, or CVS commit, and it'll do all the ones in the directory. And it'll ask for a message on this, which you can specify either as a -m argument on the command line, and tell it what is new, what bug you fixed, or what feature you added, or what's new about this version. So you can put a comment there, and it'll store that in the repository. It'll also remember your name so that if you broke something, somebody can look in the repository and figure out who stored it. One thing about this command, if you don't use -m on the command line, it will pop up an editor for you to write your message in. Now, at least on my installation here, the default editor it pops up is Vi. So if you use this and don't type that and you find yourself in Vi, we'll try and figure out how to get it to pop up Emacs, which is much easier to use. If you find yourself in Vi and don't know how to get out, find a TA and they'll get you out. Yeah?
There's a global variable this dot.
This is a .rc or something for?
Dot editor, and you have to put it in the bash profile. If you set that to Emacs, then it will Emacs.
Okay. Yeah, I knew it was some variable that you have to set that, because on my machine at work it always pops up Emacs, and you don't want to be in Vi. That's CVS. It's very good for letting multiple people coordinate when they're using the same project over time and space. And a lot of open source projects now are using it over the network. You can actually check out, as well as just checking out a source tree, you can actually, if you're going to be a developer on an open source project, check out a whole CVS tree, and now you're hooked into the global source control for that project.
So when you do commit, you overwrite the old file?
When you do commit, you make a new version, so it increments the version number, stores you as the new version, and remembers all the old versions.
All right, so basically there's no risk of deleting it?
Right. When you, one of the nice features of this is that it does keep all versions, so you can back up. If you've just gotten hopelessly lost and changed lots of stuff and nothing's working, you can back up to a known good version. You can say, check out version 18, or you can check out the code and the entire code base as of this date. Okay, and it'll kind of jump back in time and give you all the pieces of that date.
So how do you specify which version it is when you're committing one? Is it just...
Oh, it remembers what the current version is, and it increments a version number.
Okay.
Okay, this, the repository remembers all of that stuff.
So this is open source software?
This is open source software, yes.
Who does all this? I mean, just put
Good people.
No. Good people a long time ago.
Are you prevented from committing if you haven't updated recently enough? That is, 2 consecutive commits where you ignore the...
No, you can do 2. You should do an update before you do a commit to make sure there's no conflicts. You can just do a commit, and if there are no conflicts, it'll go through. But if there are conflicts, it'll complain in confusing ways. So it's best to do an update and then a commit to see what's going on. Okay, so this will let multiple people share a source and the like. Another part of implementing a large project is just building the project. Okay, this is if you have lots of files, lots of libraries put together, people are changing them, people are updating them, and you periodically want to do testing, you want to make sure the thing compiles periodically. And you just want to basically build the system. When you have 1 or 2 files, you can do that yourself, but even with a small number, as the number of the game, it starts to get confusing. And so this process is known as build process. And believe it or not, this is an actual job. Build manager is an actual job. In part of in a larger software project, there'll be people who spend all or part of their time just managing the build process of how to compile all the pieces and link all the pieces of the project together. There's a number of tools that you can use to do this. Certainly, the integrated development environments have tools to build at least your local directories. JavaSeq claims to be able to do this for you. It claims to search out all of the files you need and compile them and load them up. I have found that sometimes it does the right thing and sometimes it doesn't. Many people building something outside of a integrated development environment will use a utility called make, which was developed for Unix a long time ago and has since propagated out into pretty much all architectures, albeit in slightly incompatible forms. So there's a program called nmake, which runs on Windows, which takes slightly different input format than the program make or GNU make, which you would find on Linux. And there's another program, confusingly called nmake, from Lucent or somebody, which is, I think, slightly different than both of them. So the version we'll likely use is whatever comes default with the Mandrake, which is probably GNU make. And what make tries to do is let you organize and build large projects without having to recompile everything all the time. I mean, the simplest thing to do is to delete all of your .class files and then rebuild everything, okay? Now, if you have a lot of files, that means your debug cycle is going to take a long time. Every time you change something, you've got to rebuild everything. What make tries to do is do that more intelligently. It knows, because you've told it, what the dependencies are for all of your files. It checks when you tell it to build the thing, which you do by issuing the command make. It checks through and sees if any of your source files have changed. If any of the source files have changed more recently than the object files, it will rebuild everything until everything's up to date. And it's a nice, concise, rule-based system, a little obscure in syntax, but somewhere in the notes I've given you an example of a sample make file. They're a little odd to read because they rely heavily on macro expansion. And if people who engineer complex make files can make things that have recursive rules and are very difficult to track through, this one is pretty simple. There is some macros I defined, JFlags, and classes. These are things that just get expanded. I think this is a good scheme for your project, is just to have a variable called classes, which is the list of class files that you want to compile, and then make a target called all. Targets are typically start on a line and end with the word colon, And following the target, you have the list of dependencies. And this weird syntax is means expand the macro. So this means to make the target all is the traditional word for the major target that you want to make. It says that this depends on all of these class files. To successfully make this, you just try and make all of these things. And then you can put commands down below that are what to do. Now, if you look at my file, there's no commands after all, because once you've made all these classes, you're pretty happy.
Where do you list the classes in caps as a macro?
Right, so if you look in my example, it has complex.class, and backslash is an escape character that lets you put things on multiple lines. Since these macros only want to be one line long, you have to put backslash in your make file. And then there's these very obscure syntax rules that let you define general things, and the one I gave you is something that knows how to turn .class file or .java files into .class files. And it looks like this with then a command under it. And then just, syntax that you have to look up. In this case, @, I think is the right command, which says you want to run javac on this piece here. Okay, so I think that's what @, means. And there's an @, and there's all sorts of obscure symbols you can put in this that map into various pieces of this line. So it's good to use. This is all, again, documented on the web, and you will only need a tiny subset of the possible make power to be useful. But it is enormously handy to be able to just say make and have your program automatically rebuild all the things that you've changed. And you can even put in here something that automatically, once it builds it, starts it up, runs test programs, and spits out results. So you can put any number of commands in here. One thing I should add is all this stuff goes in a text file called the make file. And the traditional name for it, the default name, is called makefile. Okay? So if you just say make on your command line, it will look in the current directory for a file called makefile and use the commands in that. There are options that you can call this something other than makefile and have it work also.
Well, what does this last command do?
Which one?
On the board?
This mysterious thing here?
Yeah.
What this tells it to do is, this is how to make any .class file out of a Java file.
So it takes a Java file, makes a file.
Right. And it does that by it expands this weird macro and applies that rule. It just says to make a .java file from a .class file, because it's much easier to do that than having to write for otherwise you'd have to write for every one of your class files. You'd have to write a rule that says to make, complex.class from complex.java, run javac, blah, blah, blah. This lets you compress all of those rules into one at the price of a totally obtuse syntax. So once you have this technology going, it's a good thing to start to have an organized system. If once your project comes to the point where all the sub pieces are starting to come together and work together and actually become real, most projects will have a periodic build process, usually nightly, so that there'll be some automatic or semi-automatic process. I used to run it just before I went home. I would start a process that would do a build and test. Some people would have just a job that would run once every night at midnight that basically clears out or does a checkout from the CVS tree and runs the whole build process over it. This may be overkill for your project, maybe not, but this is what would typically happen in a industrial project. And so you want to check every night whether the build still works, okay? As long as everybody's careful about checking things into CVS and careful with their testing, it should all go forward. And if it doesn't go forward, you would want to know. So, typically if the build breaks, email is sent out to everybody, and there's a little witch hunt the next morning that to find the responsible party. Yeah.
Sorry, I mean, presumably, at least in the early stages, you're going to get all kinds of. You're going to get a build which needs to implement empty functionality. So, is part of the design just doing a set of dummy data to swap around for the functionality that's not there yet?
Certainly, making a nice thing to do is to make a set of kind of empty classes and interfaces at the high level, so all the pieces will kind of compile together and build together, even if they don't do anything. It's a very useful thing to do to get this process running early. Or you could just not start to invoke this process until the pieces have built up to a sufficient point. Or each subgroup could do something like this separately. It depends on the scale of the project and how it was coming along. And testing has a design phase in it as well. You need to come up with a test plan based on your specification of how you're going to test the functionality that this thing is supposed to implement based on the specification. And then for each of the subunits that you've divided it up into, each one of those needs an independent test plan, and you want to test those independently. That's known as unit testing. And then you finally want to combine them and test the whole. And then as you are implementing, I cannot emphasize too strongly the benefits of incremental testing and implementing. The more things you implement before you start to test, when things don't work, that's the more code that you have to find a bug in. So if you build one thing, test it, build another thing, test it. And the testing wants to be done, and the implementing usually wants to be done bottom up. So the things with the least dependencies, you would build and test first, and then modules that depend on those, or classes that depend on those, you would then build and test, because if you assume that these work, and you're testing this whole group, and it doesn't work, you can be pretty sure that all the mistakes are in here. Okay? And then you build up more complex units from this, and hopefully, when you get to the top, you've got these very high-level pieces of functionality. You're gluing them together at a very high level, and you only have to think of it at that level when you're trying to test it. So testing is a constant part of the implementation and design process. And often you want to link it into the build process. So you have a test suite of things that it does and some way to tell whether it succeeded. So once you have something like that, you can integrate it into your build process. So every night or periodically, you not only make your entire subsystem, but you run the test. All right? And then you can keep that integrated or up to sync with your source control. So you can tell when the last version was that this test worked, and track when things suddenly stop working, and then you can either fix it or back up to a known working version and continue. It's good to be explicit in your test plan, and as I say, there's a serious design phase in the test plan that relates to how you test the specification. In a larger project, an industry project, this is another whole job. Or maybe, there might be 2 or 3 people just doing this. And their goal is they're given the specification, they come up with a test plan and a test harness and tests, and then the implementers who are over here then give their completed thing to the testers, and the testers run it through their paces and tell you whether it worked or not and track your progress. Separating these things is both good because this is a hard thing to do and is a legitimate specialty, and also it keeps the implementers from saying, oh, I know this works, I won't test this functionality, and from being sloppy. So this is a whole, usually there's a whole organization in software that will do just that.
This guy who shot all these guys, he wasn't testing. Oh, what was that?
Over Christmas, the day after Christmas, he shot 7 guys.
I assume that does not reflect in any way on the job of QA. One last thing I want to say just a few words about is debugging. It's hard to really teach debugging since it is really something it's a skill that you have to learn by experience. But there's some general rules that are good. First of all, the incremental build and test really will save you a lot of trouble. If you do have something that doesn't work, one of your goals is to kind of trap the bug. Okay? If you have a lot of code and you don't quite know what's going on, you want to essentially disable or disarm one piece after another. Okay? Simplify it so you can still run this test, and eventually you should get back to the point where you're at a known working, where everything works the way you think it would be. Okay, for the functionality that's there. And then you start little by little re-enabling stuff and see where it breaks. And once you've found when you've enabled something and it breaks, okay, you've kind of narrowed down where that bug is, and then you stare very carefully at that and see if you can find what's wrong. Another good idea is to just not change things randomly. Debugging is essentially a diagnosis process, okay, similar to auto diagnosis or medical diagnosis. So you want to use science, okay? You want to think about what's going wrong, think about how you're doing things, and form a theory. Come up with a theory in your mind of what's going wrong, okay? And once you have that theory, then you want to make an experiment or test to confirm or deny that theory. So if you think that this line should be changed, do something else. You change that one line and only that one line, or you think that this line is all the trouble, you just comment out that line and only that line, run an experiment, and see if that theory is correct. If the bug is still there after you've commented out that line, clearly your theory was wrong. If everything works, or with limited functionality, then clearly there's something wrong with that line and you've got to go fix it. So use science. Come up with a theory, come up with experiments to test the theory, and execute the experiments. Change one thing at a time, see if it helps, and then just work your way through it. Don't change 10 things at once, because if things suddenly start working, you don't know which one of the things you fixed or you changed fixed it. And it's very important when you have a difficult bug to understand what it was and fix it and know why you fixed it and know why the fix works. Because if you change things and stuff magically works, sometime down the road that bug is going to come back, and in usually a more virulent and annoying form. So understand, and when you find something that's particularly obscure or difficult, put a comment in to make sure nobody else says, why did they do it this way? This way is so much better, and rewrite your code to put the bug back in after all your hard work. Or just if it appears someplace else, you'll remember the fix. So when you spend a lot of time debugging something and finally get an answer, put a comment in near the fix that explains it all. And also when you check it into CVS, explain it all. That's, I think, my perspective on the process. Alan will talk a little this afternoon about his perspective. He's worked in different environments than I have and has his own view of the process and how it proceeds. And in some places it's much more chaotic than this, and you skip a lot of steps. And in other cases it's very rigid and formalized, and you have huge groups associated with all these steps. And this process is a tool to use to keep things on track, not meant to annoy and get in the way. But experience has shown that this sort of thing definitely is progress in the way to do things. I guess that's all I have to say. So good luck with your efforts, and we will be coming around and talking to you about your designs and progress and stuff.